Hello, this is our fifth lecture of this series in the course of organic photochemistry. In the previous lecture, what we have discussed we are discussing about the photochemistry of carbonyl compounds. We mentioned last time that the photochemistry of carbonyl compound is extensively studied. It has a very strong absorption between 230 to 40 nanometer and 240 to 340 nanometer, and hence the carbonyl compounds, depending upon the substituent, undergoes four different types of photochemical reaction. Number one, aliphatic carbonyl compounds undergo Norrish type 1, which involves alpha bond cleavage; Norrish type 2, which involves abstraction of gamma hydrogen by excited carbonyl. Third type photoreaction is photoreduction. This is common in aromatic carbonyl compounds like benzophenone and so on. And the fourth reaction of carbonyl compounds is the cycloaddition with alkenes, that is known as Paterno-Bucchi reaction. It leads to the formation of four-membered oxygen-containing heterocycle, that is oxetane. We have already started previous lecture the photochemistry of type 1, Norrish type 1 reaction, by taking the different products formed in aliphatic aldehyde, aliphatic ketones, and so on. And then we now start with the Norrish type 1 reaction in cycloalkane. Norrish type 1 in cycloalkane. The cycloalkanes, alicyclic ketones, also undergo type 1 reaction. And we have also looked the one example in the previous lecture, cycloalkanone. The cyclobutanone. Cyclobutanone undergoes first step is the alpha bond cleavage. Then the diradical form after alpha bond cleavage, the acyl radical and carbon center radical, undergo three different types of photoreaction. First one is decarbonylation, second one is beta cleavage, third one is the ring expansion reaction. Now we are looking few more examples in the alicyclic ketones, type 1 reaction alicyclic ketones. This is once again cyclobutanone, but here the one of the alpha bond, alpha carbon, is substituted with dimethyl groups. So in the presence of light, this undergoes the first step is the this in the presence of light and goes type 1 reaction, which is the nothing but is the alpha bond cleavage. So there are two alpha bonds. This is also alpha bond, this is also alpha bond. So we'll just see the cleavage of both the bonds and see what type of radicals form is. If we cleave this, we get this carbon center radical and this acyl radical. If we cleave this, we get this acyl radical and this carbon center radical. If we look at the stability of this carbon, this is common in both the cases. The stability is decided by this carbon center radical. So here you can see this is a primary carbon radical and this is a tertiary radical. So we know that the order of stability of radicals lies in the order tertiary is more stable than secondary, is more stable than primary, and hence if you look at so this will undergo, when the alpha carbon is substituted, then we have to the first step, that the alpha bond cleavage, there will be a preferential alpha bond cleavage to give you more stable carbon center radical. So this will cleave preferentially this bond to give this radical and not the less stable carbon center radical. And now this is open for the different products, as we have seen in the first in the last lecture, where you undergo 3 different types of reaction: A, B and C. A is the decarbonylation minus CO. Then this will give you this will give this radical after the decarbonylation minus CO, and then this will combine to give the cyclopropyl radical. So dimethyl cyclopropyl radical. The path B is the beta cleavage to give like this. So you have a disubstituted alkene plus a ketene, and then this will of course decompose to give ester on reaction with the alcohol. So this gives ester. And third type is the ring expansion product, that is this radical will add to this oxygen to give a carbene, the carbene intermediate, and then this carbene in the presence of alcohol gives rise to this product, the ring expansion product, 5-membered oxygen containing heterocarbonyl ring expansion product. So what we have seen, that when in the case of alicyclic ketones or cycloalkanones, when the alpha carbon is substituted, then this will undergo preferential alpha cleavage in the type 1 reaction, type 1 photoreaction, to give a more stable carbon center radical. As we can see here, if we cleave this bond, you get a primary radical is less stable, and this is more stable, and hence the more stable carbon center radical will form and for what leads to the product. Now we'll look few more examples of this alpha, where the alpha carbon is substituted. This is the series of cyclobutanones with the different substituent at alpha carbon. So we have 1, 2, 3, 4 and 5 examples of cyclobutanone, and then this we are looking into the photo addition, photo reaction. All will undergo type 1 reaction. All will undergo type 1 reaction, and then in all these 4 cases, the alpha carbon, one of the alpha carbon is substituted with different substituent. Like here, the cyclopropyl is a pyrotype compound. Here, cyclopropane is present as a substituent, whereas there is a presence of a double bond in one of the carbon. Again, the double bond is connected with the cyclobutanone ring. Here, the double bond is present as a substituent. Again, here cyclopropane is a bicyclic ring system, and so on and so forth. So one by one we will look. So as usual, we have seen in all these cases undergoes first is the alpha bond cleavage. First step, alpha bond cleavage, and we have also learned in the previous slide that alpha bond cleavage is preferential. When the one of the alpha carbon is substituted. So, and more stable carbon center is going to be formed, and which will lead to the product. So in all these cases, we are just going to look into the first step, preferential alpha bond cleavage, and second is we are going to look only the ring expansion product, only ring expansion product. Of course, it will undergo decarbonylation as well and also undergo decompose to give ketene. But just for one of the most important step here is the decision to decide which, since one of the alpha carbon is substituted, hence the foremost important thing here is to which alpha bond is going to cleave, and this will be decided by the stability of the carbon center radical, because in all the cases you have a different substituent. One of the there are two alpha carbon. This is also alpha carbon, this is also alpha carbon. Alpha carbon is also, one of the alpha carbon is substituted, other is not substituted, and hence the cleavage is going to be preferential, and hence so we are going to see the first step, which is going to be more important, and then of course once you have decided we have correctly cleaved the first step, that is the alpha bond cleavage, and then next step is simple decarbonylation followed by a cyclopropyl 1,3 diradical, and then recombination to give cyclopropane. Second step is the beta cleavage to give alkene as a neutral product and ketene as the intermediate, which decomposes in the presence of water to give carboxylic acid, and ester in the presence of methanol to give an ester. So in all these cases we are going to give which bond is going to form, and we are going to look only the ring expansion product, which is very important after the cleavage. So this is the first example. The cyclobutanone is substituted by a cyclopropyl group, is a spiro. This is a spiro type compound, and now this is alpha bond. This is also alpha bond. We are going to look the photo reaction, which is cycloalkanone. We know that it will undergo type 1 reaction. Type 1 is alpha bond cleavage, and since one alpha carbon is substituted, another carbon is not substituted, there are two hydrogens here, so it has to be going to be preferential cleavage. Let us cleave this bond A, and then say this is B. The first cleavage of A is going to give you this, and cleavage of B going to give this. So we are going to see this is a primary carbon, and this is a tertiary carbon. So according to our earlier assumption, we know that the order of stability of radical lies in the order tertiary is more stable than secondary, and then is more stable than primary, and then is more stable than CH3 radical. This is the order of stability of radical. So, but this is not always true. Here cyclopropane, we know that is under ring strain, and the bond angle is around how much is around 60 degrees, and this is a lot of deviation from all our tetrahedral carbon, 109.28 degrees, and hence it is highly understand. That's why a banana type structure has been proposed in the cyclopropane, and since cyclopropane is already under strain, we are going to generate a radical on the cyclopropane ring. So the radical on the cyclopropane is again going to be destabilized by the presence of because of the high ring strain. Radical on the cyclopropane is very difficult to generate, and hence is less stable, radical as it is on the cyclopropane ring. And that's why, although it is a tertiary radical, but it is less stable because it is present on the cyclopropane ring, and hence it is not going to form. So this is radical, although it is a primary, and hence it is going to be formed. So what we have learned is this is not always true, but is also there are other aspects which are also looked into to decide the stability of this radical. Here we can see that the radical is going to be generated on the cyclopropane ring, and since the cyclopropane is under high strain, the generation of a radical on the cyclopropane ring is difficult to generate, and hence is not going to form. And this, although it is a primary radical, is going to form, and this will lead to the product. So we have we would like to see this will as usual undergo three different types of reaction. A is the decarbonylation, B is the beta cleavage, and third is the ring expansion products. So we are going to look the ring expansion product at present here in all these cases. So this radical is going to attack on this oxygen, and this is going to shift like this. So it's going to generate a carbene radical here, carbene, and then in the presence of methanol, because this is a solvent, photolysis is carried out in this solvent, and then this is the ring expansion product which is going to be formed in this. So what we have seen in this example, that although the one of the carbon of cyclobutanone is substituted with cyclopropane ring, is a cyclopropane ring is present as a bicyclic system, as a spiro compound, and alpha cleavage is going to be, it has to be a preferential alpha building cleavage, because we have seen the more stable radical is going to form when one of the carbon is substituted, and hence here we have seen that the radical is going to be generated on the cyclopropane ring. Cyclopropane ring is under strain, and generation of a radical on the strain ring system is difficult, and hence it is not going to form, and less stable, that is the primary radical is going to form, which will lead to the ring expansion product. For ring expansion product, this will add to oxygen, this will shift as to give a carbene, and then in methanol going to give you this product. So now let us see the second example of this series. This is the second example where the cyclobutanone is one of the carbon. This is alpha carbon, is also this is also alpha carbon. One of the alpha carbon is substituted by the cyclopropyl group. Now look at this. This is the difference between the earlier example. This is a spirotype substituent. This is the cyclopropene is present as a substituent in this case. So and of course we have seen that when the alpha carbon is substituted, we going to be preferential cleavage. This is going to be cleave. We'll see one by one. Cleaving this, we are going to generate a radical here. Cleaving this bond, we are going to generate a radical here. This is a primary radical, this is a secondary radical. Here the radical on the cyclopropane ring is going to be stabilized. Cyclopropane is considered as equivalent to a double bond. Hence radical adjacent to a carbon, radical adjacent to a cyclopropane ring is stable, and hence this is going to be preferentially cleavage is going to be formed. This is a primary radical, is going to more form, not going to form, and hence this will lead to the ring expansion. So look at the difference. Cyclopropane is a substituent here. Radical is generated on the carbon adjacent to the cyclopropane ring. Cyclopropane ring, this radical is going to be stabilized in the presence of cyclopropane ring. Cyclopropane ring is considered as a double bond, and hence anything, any radical or the positive charge or a negative charge adjacent to a double bond is going to be stabilized due to delocalization, and hence this is going to form preferentially, and this will lead to the ring expansion product. Not only the ring expansion, it will also undergo three different reactions. First step is decarbonylation, to give a 1,3 radical, and this will combine to cyclopropane ring. This will undergo beta cleavage to give an alkene with the cyclopropane ring plus ketene, and this will decompose in the presence of water to acid and ester to ethanol or an ROH to ester is acid. So ring expansion product, for the formation of ring expansion product, this radical is going to attack on this oxygen. This will move here to give as this as a carbene intermediate, and then in the presence of methanol. So this is the possible ring expansion product in this particular case, that is cyclobutanone, where cyclopropyl group is present as a substituent. So I hope this is clear because in both the cases cyclopropane is present as a different example. Here cyclopropane is like present as a attached to the 4-member ring. Here cyclopropane is present as a substituent, and hence this makes a difference. The radical on the cyclopropane ring is destabilized, although it is tertiary, is not going to form. Primary radical is going to form, and this will lead to the product. In the second case, cyclopropyl is present as a substituent, and radical is present on the carbon adjacent to the cyclopropane ring, is going to destabilize, because cyclopropane is considered as a double bond. Anything adjacent to a double bond is going to be stabilized due to delocalization, and this is primary radical is not going to form. This will lead to the different products of photoproducts, decarbonylation, beta cleavage, and ring expansion product. What we have seen in the earlier, that in all these 3 cases we are going to look only the ring expansion product, because the first step is going to be a deciding factor to decide in which bond is going to be. If we make any mistake in the first step, the ring expansion product will end up with the wrong ring expansion product, and hence our answer will be wrong, incorrect, and hence this is the ring expansion product is going to form, is going to be stabilized. Now look at the third example. So now again this is a cyclobutanone. Double bond is attached to the cyclobutane ring, and it is not as a substituent. So that is, we have to just keep in mind. So this is alpha carbon, this is also alpha carbon. Photolytic condition, this will undergo type 1 reaction. Type 1 reaction is nothing but is a alpha bond cleavage. So either it will cleave this or it will cleave this, and hence we have learned that when one of the alpha carbon is substituted, it will undergo a preferential alpha bond cleavage to see which carbon is going to be which radical is going to be more stable, and hence if we cleave this, we end up with this radical, and if we cleave this, we'll end up with this carbon. It is a primary radical. This radical is on the double bond. This is sp2 hybridized carbon, and the generation of a radical on the sp2 hybridized carbon is unstable, and is not going to form, because generation of a radical on the sp2 hybridized carbon is not going to be stabilized and unstable, not going to form. So hence the primary radical is going to form here, and this will lead to different photoproducts. This will as usual lead to decarbonylation, beta cleavage, and ring expansion product. This radical is going to attack here, moving off a double bond to give this carbene as a intermediate, this in the presence. So this is the ring expansion, possible ring expansion product in this particular case. So here if we make any difference in by cleaving this one, so this is going to cleaving this one, saying that so this will lead to a different ring expansion product. So in this case also there is going to be a preferential alpha bond cleavage in photochemical reaction of cyclobutanone, where one of the carbon is substituted by presence is attached to a double bond. One of the carbon is substituted with double bond, hence a radical on the double bond is going to be destabilized, is not going to form is not going to cleave, and then is going to be preferential cleavage. Preferential cleavage of alpha bond takes place. In this particular case, going to give you a primary radical, and this will give you a ring expansion product in this particular case as well. Now again going to next example. This one, here again this is double bond is present, but there is a difference. This is the third and fourth example. Cyclobutanone as usual will undergo photo reaction, type 1 reaction, alpha bond cleavage is one of the, it is alpha carbon, is also alpha carbon. One of the alpha carbon is substituted by the double bond, and hence is going to be a preferential cleavage. Preferential cleavage. So now look at the difference. This double bond is present as a substituent. This is different from this one. This double bond is attached to the cyclobutane ring. This double bond is present as a substituent, and hence let us cleave this, going to give you this radical, and now here this radical is adjacent to a double bond, is going to be stabilized by the presence of a double bond. If you write destabilized structure, stabilized structure, it will come like this. So the radical adjacent to a double bond is stable, and hence is going to, of course it is a secondary radical adjacent to a double bond is stable, is going to form the photoreaction is going to be a preferential alpha bond cleavage, and this is a primary radical is not going to form because it is more stable, and the two factors, one is a secondary radical, and third second region is adjacent to a double bond. The other stabilizing factor is the adjacent to a radical on the carbon adjacent double bond is going to be stable, and hence is going to form a ring expansion product by attacking of this radical to this oxygen, and then this will go like this, and then we can see here is oxygen, this carbene is going to form here. This is the double bond, and then this will lead to the product ROH, going to give a product like HOR. Of course, we are not bothered about stereochemistry here. So this is the correct ring expansion product in this plane. So in this is also the first stage is very important, and we should recognize that this radical, which radical is going to be stable, and where the substituent is going to stabilize or destabilize. The radical, what we have seen, that radical on the cyclopropane is destabilized. Radical adjacent to a cyclopropane is stable. Radical on the double bond is unstable. Radical adjacent to a double bond adjacent is stable. So just to summarize what we have seen here, number one, if you generate a radical on the cyclopropane ring, if we generate a radical on the double bond, is unstable, is unstable, whereas in other case, radical adjacent to a carbon, a cyclopropane ring is stable. radical adjacent to a double bond is stable. So these are very important aspects in order to proceed for the first step. This is going to form, this is going to form, this is going to not form, this is going to not form. So hence other double bond will cleave, where it is going to give you a primary radical, and this will lead to the further product. So we stop here, and then we will see a few more examples of the type 1 reaction. These are all different substituted cycloalkanones, where we have a bicyclic system with a carbonyl, and hence what are the different products derived from this, we'll see in the next lecture. Thank you very much.